The last section of the chapter 4 is optimization. Optimization theory is actually much more than I will explain in this video. And business and economic students will focus on these topics with more detail in their future courses and their professional life. In this course, we will go over some simple optimization problems using the knowledge you learn in this course. As you know, these videos only contains the lectures about the subject. We do the detailed solving example in the classroom. Now, we can use calculus to solve optimization problems. Problems that involve finding the absolute maximum or the absolute minimum of a function. As you work throughout this section, note that the statement of the problem does not usually include the function to be optimized. Often, it is your responsibility to find the function and then to find the relevant absolute extremum. So, the procedure you should follow when you see the optimization problem is the following one. So first of all, in the step 1 as it's indicated, you should introduce all variables. Okay, look for relationship among the variables and structure of mathematical model of the form. So we will find the objective function, that is our aim function. Okay, this is objective function. This should be minimized or maximized on the some interval. So this interval generally called as a constraint. In the second step, you should find the critical number for the function f of x. If the interval which is indicated in the step 1 is closed interval, as you know, all functions have absolute maximum and absolute minimum. On the closed interval, all continuous functions have their extreme point. So, by finding critical point, you can discuss the minimum or maximum. So in step 3, use the procedure developed in the section 4.5 maximum and minimum procedure, okay, to find the absolute maximum or minimum of the function f of x on the interval I and the number x where this occurs. And in the last step, use the solution to the mathematical model to answer all the questions asked in the problem. The technique used to solve optimization problem are best illustrated throughout the examples. Okay, so let's look the following example. Let's read first of all. A homeowner has $320 to spend on building a fence around a rectangular garden. 3 sides of the fence will be constructed with wire fencing at a cost of $2 per linear foot. The 4th side will be constructed with the wood fencing at a cost of $6 per linear foot. Find the dimensions and the area of the largest garden that can be enclosed with $320 worth of fencing. Actually, this figure give us some information according to the question. So we don't know this length and we don't know that length, but our aim is to build a fence around a rectangular garden. This is rectangular garden, okay? So let's say this length is y, that length is x. So let's denote this length is x, this length is y. So the cost of the this tree length is $3 per foot. And the cost of this length, this is the wood fence thing, is $6. So, generally, in the optimization problem, I recommend to draw a figure like this figure. Sometimes it can be given, sometimes it cannot be given. And introduce your variable. Here our variable are x and y as you see we introduced. And look for relationship among the variables. If there is some relationship, okay? Since we don't know the dimension of the garden in this question, the length of fencing are represented by the variables x and y. The cost of the fencing material are fixed and are represented by the constants. Now, we look for relationship among the variables. The area of the garden is x times y. But this our aim is not to maximize or minimize the area. Okay, our aim is to maximize the area. That's our aim, objective function, but it has two variables. Okay, x and y. But on the other hand, we have some constraint. We have some restriction. What is our constraint? Our total budget, our total cost should be $330. Okay. So, what is the cost? The total cost. The total cost is the cost of this length, $2 for per foot. So this is the y foot. So 2 times y. The cost of that part is 2 times x dollars. And the cost of this part is again 2 times y. Plus the cost of the wood part. The cost of this part is, this length is x, so 6 times x. So as a result, the total cost is 8x plus 4y. And what we know that the total cost is $320. Okay. So in the problem, it's stated in the problem, the homeowner has $320 to spend the fencing. So we assume that enclosing the largest area will use the all money available for the fencing. Okay. So the problem has now been reduced to one variable case. Okay, so actually our problem is that one, maximize the area subject to this constraint. Okay, according to the procedure, we write our equation. Okay, maximize, minimize f of x on the interval. So this describes the interval actually, but by using constraint we will describe. In more general case, optimization problem indicated as this way. Okay, objective function and the constraint. But what is the constraint? Constraint is not this 8x plus 4y. I am sorry. The constraint is 8x plus 1 equals $320. Okay. So by solving cost function, cost value, we can interpret y in terms of the x. So y equals 320 minus 8x over 4, which is 80 minus 2x. So, by replacing x in the area, we can obtain the one variable function. This is two variable function. Area depends on the x and y. You don't know what is two variable function. Maybe you are not familiar to this notation, but area depends on two variable x and y. So, by replacing y with 80 minus 2x in this equation, we obtain one variable function. Okay, so the area equals, with respect to x, I will interpret x times what is y, 80 minus 2x. So this is 80x minus 2x square. So we will maximize this area function. So, but what is the domain? What is the our interval on the interval I? So for the interval I, x have to be bigger than 0 because it is the length, and y have to be bigger than 0. So the interval or domain of the f of x include the x variable. So from the fact y bigger than 0, since y equals 80 minus 2x, 80 minus 2x bigger than 0, bigger than equal than 0. So this implies x is less than 40. So as a result, our interval is the closed interval 0 and 40. So x change between 0 and 40. If x is 0, just you have a line. The array is 0. If x is 40, again just you have a line because now y is 0. So x will change between 0 and 40. If x is 0, y is 18. So the total cost 18 times 4 times 18. So this is 320. And if x is 40, y is 0. So 8 times x is again 320. You can verify the cost earlier. So our aim is to maximize the area on the given interval. Okay. So let's emphasize this is our aim to maximize. So next, we should find any critical numbers. Actually, just this is the step 1. First step or second step. Step 1 is the introduce the variable. Okay, let's write the equation. So in the step 2, we should find the critical points. So derivative of the a with respect to x equals 80 minus 4x. Okay, from here 80 minus 4x. So what is the critical point? Critical point is derivative of the a of x equals 0 implies 80 minus 4x equals 0. This implies x equals 20. So this is a critical point. So in the step 3, use the procedure developed in the section 4.5 to find out maximum. We can make the sign chart in the step 3. Step 3. So let's make the sign chart. X, the domain of the x is 0 to 14 and the critical point is 20. So here derivative of the area is 0. And if x is, for example, less than 20, you can check for value 10. Derivative of the a is positive. Okay, if x is 10, this is positive. If x is 30, this is negative. Okay, so positive, negative. So the function a of x, increasing, decreasing. So at the point 20, there is a maximum. Local maximum actually. Local maximum. But on the closed interval, by observing the a of 0, a of 20, and a of 14, here 0 is the end point, 14 is the end point, 20 is the critical point. So a of 0 from the function 80x minus 2x square, let's write here, maybe you can forget, 80x minus 2x square. So for x equals 0, a of 0 is 0. For a equals 20, 80 times 20 minus 2 times 20 square, 1600 minus 400, 800. So this is 800. Okay. And e of 14 is again 0. You can calculate 2 times 40 square. So this is 0. So as a result, a of 20 is the maximum value of a of x function. What is the maximum value? 800. So 800 foot square is the maximum area you can build a garden. So finally, we must answer a question posed in this problem. The dimension. Also, if in the question, what is the asked? Let's look here. Use the solution of the mathematical model to answer all questions. So in this step 4, we should give the answer. Find the dimension and the area. So, okay, this is the correct. Step 3, just I wrote for the area. Step 4. So for the dimension, we can say that the dimension of the garden with the maximum area of 800 square feet are, what is dimensions? X is 20, so x equals 20 feet by y equals, we can calculate quickly here, 80 minus 2x, y equals 80 minus 2 times 20, which is 40 feet. Okay. Maybe we can give more explanation for the wood fencing part. With 120 foot, this is the x side, foot side of wood fencing.